Okay, hello again. And in this example, we will be calculating the net electrostatic force and direction on the positive 2 microcoulomb charge located on the top corner of our isosceles triangle. At the base, I have a positive microcoulomb 7 and a negative 7 microcoulomb, and the distance between each two charges. For the first part, I need to calculate the force. I need to calculate the electrostatic force generated. Let's say this is Q1, this is our Q2, I will call it, and this is our Q3. Okay, so let's calculate F12, that's the force on 1 because of 2. It's going to be 8.9, 10 to the power 9, multiplied by 7, 10 to the power minus 6, and 2, 10 to the power minus 6 again, divided on the distance, which is 5 meter squared. When you do the calculation of this one, it should be very, very close to 5, 10 to the power minus 3 Newton. Okay, now definitely because of the magnitude of the charges we have and the distance between each two charges is equal, that will make it simpler for us that the force on 1 because of 3 will equal the force on 1 because of 2. So we know this one also, it's a 5 10 to the power minus 3 Newton. Now, to determine the direction of the electrostatic force generated by each charge on Q1, let's try to draw the direction. So the force on 1 because of 2, they are both positive charges that will generate a repulsive, which means it's an extension of the line between them. And that will be the force on 1 because of 2. Now, for the Q3 and Q1, there is a negative and positive charge that will be an attraction or attractive force, and that will be F1, F3. Okay, now to distribute the direction, or analyze these vectors into two components, what we need to do is I will call this angle as beta. So if I want to analyze this force, that will be force 1, 2 cosine beta, and here I will have the force on 1 because of 2 sine beta. Now let's use the same color. Let's pick, this is our angle, and I will call it alpha in this case. So let's analyze our force on 1 because 3. That will create F1 3 sine alpha, and to the negative y-axis I will have force on 1 because of 3 but cosine alpha. Okay, now to help us finding the values of every single components here, we need to find these angles alpha and beta, and to do that I will split our isosceles triangle into half, so I will have two right angles. So I'll start with the first one. So if I draw this triangle here, that's here Q3, this is still Q1, nothing changed, and I know, let us change the color, this one will be 3 meter because it's half of the base, this one is 5, and the height will be 4. This is still our alpha angle. Now if I want to find the sine of alpha, the sine of alpha will be simply it's a 3 over 5. If I want to find the cosine of alpha, it will be 4 over 5. Okay, which means I can easily now calculate how much is the force on the component x-axis of 1, 3, and same for f13 y component. So if I want to say, okay, that's f13, the x component, that will be the magnitude, which is the 5 millinewton, and multiplied with the sine alpha. So I multiply it with the 3/5. That will give me total 3 millinewton. For the y component of the force on 1 because of 3, it will be again the magnitude of that force 1 on 1 because of 3 multiplied with the cosine, which is here, this one, cosine alpha, and that will be multiplied by 4/5, giving me 4 millinewton. Now I need to remember the direction can be to the negative y-axis or south, so I place that negative to remind me about the direction. Now to continue with the other angle, which is beta. Now based on our knowledge from the triangles, this angle here will be acting as beta as well. So simply I can do this. This is my triangle. This is my angle beta. That's the 5. Still, this is the 4, and half of the base, because we split it, it's going to be 3. Now, once again, if I want to find sine beta, it will be 4/5. If I want to do cosine beta, that will be 3/5. So, if I want to find how much was the f12 x component, it will be again the magnitude 5 milli, and once again, just in case we go back, the x component was with the cosine beta. So there was here f12 cosine beta. So, and the cosine is 3/5. That will give me 3 millinewton. Okay. Now, to do the same thing for the y component of the force on 1 because of 2, which was up here, I will have the magnitude multiplied by 4/5, and that will give me the 4 millinewton. That's excellent so far. So basically what I have two components going to the x-axis, which is the f12x and also f13x. So if I want to add them up to find the total forces on the x-axis, I'm gonna add this term with also this one. So what I will have 3 millinewton plus 3 milli, and that will give me 6 × 10⁻³ Newton. Now for the y-axis, what I will change the color. I will have one going up, which was the f12y, and also I have the f13y, which is, that's mean if I want to calculate the total force on the y-axis, I will have the f12y and add to this the f13y. And to do that, we will find that I am doing 4 minus 4, and I will end with a 0 Newton. There is no force on the y-axis because they're equal in magnitude, opposite in direction, they will terminate each other. So the net electrostatic force on that charge will be simply the fx squared plus fy squared and you will find it is again, it's the 6 10 to the power minus 3 Newton. Now, in terms of the direction, well, we can see that the only components remained acting or affecting on that charge is only the one going with the x-axis. So simply we can say theta, or I can do it in another page. So direction of the net force will be theta equal 0 degree. So it is to the east, or you can say positive x-axis. So in this video, I try to show you how we can find the net electrostatic force using a triangle shape where charge being distributed, but it's a different triangle than the video before, and the magnitude of these charges is different. So it's a different technique to get the answer, but as a concept it will be following the same thing. I hope you find this example useful, and we'll see you again in another video. Thank you.